Right, so the nitration of benzene. Step one is making the electrophile. And we've done that with these equations up here. So you've got the sulfuric acid, which will act as the acid, so it donates its proton, the H+. It gives that H+ or proton to the nitric acid, which, just to confuse you, is acting like a base. Just there, it's accepting the proton because plus H+, to make the horrible H2NO3 plus ion. The H2NO3 plus ion is going to decompose in water, sorry, it's going to produce water, H2O, and NO2 plus, which is going to be our electrophile. So it's an electrophile because it's got a positive charge. It's going to be attracted to something negative. Now, here we've got our benzene ring and our NO2 plus. I put the plus on the nitrogen because that's what actually has the plus charge. So, when we did, and we know it's going to be an electrophilic attack, so it's going to be attacking the electrons, or the negative charge. Where is there a lot of negative charge? In a benzene ring, in that delocalized area of electrons, which we represent on the skeletal diagram as the circle in the middle. So, this electrophile, the NO2 plus, is going to attack the electrons in the delocalized p orbital ring thing. So how are we going to draw that? Well, your curly arrow always has to move from a pair of electrons, or from the electrons, to wherever the electrons are going. So our curly arrow has to start on the delocalized ring, and it has to go to the nitrogen. Like that. Simple. It's the same as when you do electrophilic addition, you draw it from the double bond to the the H on the hydrogen halide, or the halogen on, where it's attacked by a halogen. Now, what is that going to make? We have to draw an intermediate stage. We don't break any of the carbon bonds around the outside. So we've still got the hexagon. But what we have done is broken the delocalized electrons. We've broken those overlapping p or pi orbitals. So how do we show that on one of these diagrams? Well, you just draw your ring, but not complete. So I normally just draw half a ring. Now, it is really important that you put this ring in the right place. And I'm going to tell you where you need to put that ring in a minute. So, when this NO2 plus has attacked the ring, the delocalized ring, it forms a bond. And it bonds onto one of the carbons on the benzene ring. It's also really important at this point to remember that this is a skeletal diagram. So it doesn't show the carbons, that's just where the straight lines meet, and it doesn't show the hydrogens. But technically each of the corners on this hexagon has a hydrogen on it. I haven't done anything to remove the hydrogen that was on this same carbon that the nitrogen, or the NO2, the nitro group, is attached to. So the hydrogen is still there. And this time we do actually draw the hydrogen on because it's going to get involved in the mechanism. So there's a couple of other really important things that we need to do. First of all, look at the location of this broken ring. This carbon that we've attached the nitro group to, we're going to call carbon number 1. And therefore this is carbon number 2, and this is carbon number 6. This partially filled ring cannot go past carbon 2 or carbon 6. It can be as small as you want, or it can be as big as you want, as long as it doesn't go past 2 and 6. That's just the rules, because the part of the ring it's broken is around this carbon, which now has bonds to the nitrogen and bonds to the hydrogen. This carbon, carbon number 1, that is the one that doesn't have any spare electrons to put in the p orbital and to contribute to the delocalized ring. So the ring is broken around the 1 carbon. And the other thing that you might have noticed is that in this first part of the reaction, the benzene's got no charge, but the NO2 does have a charge. Now we've got this whole molecule here, which doesn't have a charge. And the only reason it doesn't have a charge is because we haven't drawn it on yet. And it's got to be a positive charge because the charges have to balance. And where have we taken the electrons from? The delocalized ring. So the plus has to go in the delocalized ring. I know there are some people out there who like to think of this as a random smiley face with a couple of antennas, a big smile, and a cute little nose. Or if you really want, you can have an H and NO2 eyes as well. If you like to think of things in cartoon anthropomorphic ways, that's fine for you, but it's not good chemistry, is it? So, next step of the mechanism. We want to reform the ring. We want to make this stable. It needs to get electrons from somewhere. And what's going to happen is this carbon-hydrogen bond is going to break, and the electrons from that bond, they're going to fall into the ring. And that means this hydrogen is going to go off and escape. Now, where is that hydrogen going to escape to? If we look at these top equations when we generated the electrophile, if you think that all of this reaction is currently being done in a big test tube, if you think about what we've got in this test tube, we've got some benzene. We've got this H2SO4, which has broken up into HSO4 minuses. We've got some extra water in here. We've got some NO2 pluses. And we've also got some of these intermediates. And we've got the H pluses which have just escaped from it here. So that H plus is going to join an HSO4 to produce the H2SO4 that we started with. It's going to join with this HSO4 minus to reproduce the H2SO4. Hopefully at this point you're thinking, oh look at that, the H2SO4 was used at the beginning, it's being reproduced at the end. It's a catalyst. Yes it is. And if we look at the final product that we're making, once we've fallen in here and recreated the ring, we've got nitrobenzene. Plus the H plus, which will go and join the H2SO4 again. Now, it doesn't matter if there's anything else attached to this ring, within reason. So let's just say, for now, we're going to start with methylbenzene or toluene. This time, my NO2 plus is going to, again, attack the ring. It doesn't matter that there's a CH3 group attached to the ring already. It doesn't care. We're substituting one of the hydrogens on the ring. So anything else attached to the ring doesn't matter. However, this time, We're going to attach it opposite the CH3 group. And because we're adding it onto this carbon, the broken ring now can't go past here or here. So the broken ring now has to look more like that. So the broken ring is always open opposite the carbon that you're attaching stuff onto. And then that's going to fall into there. And you're going to end up with the localized ring being reformed, and you have got nitrotoluene, or if we're going to go for the correct name, one methyl 4-nitrobenzene. Simples.